Hello and welcome to Lecture 5 of Changing Magnetic Fields in Phys 1204. In this lecture, we're going to meet a new kind of circuit element called an inductor. An inductor is a thing in a circuit which generates a magnetic field, so it could be a solenoid or a coil or anything similar like that. And we've seen in the last video lecture what happens when we have a coil in a circuit. It tends to resist changes to the current through it, because if the current through it is, say, decreasing, then the B field inside it is decreasing, the flux is decreasing, and it generates an EMF which tends to oppose that. In other words, it tends to try to keep the current going. Similarly, if we try and increase the current through a coil, it will generate a counter EMF that essentially fights against the current increasing. On a circuit diagram, the symbol for an inductor is this loopy thing that looks like a solenoid, which makes sense since inductors often are solenoids. Well, so every inductor must have a property, which we'll call inductance, which defines it. So just like a resistor has a resistance, or a capacitor has a capacitance, every inductor has an inductance. Well, what is an inductance? What does it mean? Well, I'm going to work by analogy with capacitance. We know that capacitance is charge stored on the capacitor per unit potential difference applied across it. But here's an alternate way of thinking of it. You know that the E field inside the capacitor is proportional to the charge on its plates, like so. Or in other words, the charge is proportional to the E field. And so capacitance could also be written this way, but this quantity right here is the electric flux inside the capacitor. And so you could, other than this constant of epsilon naught here, look at capacitance as stored electric flux per unit potential difference across the capacitor. I don't really know why you would define it that way. It's not a particularly convenient definition, but there's nothing wrong with such a definition. Well, we're going to define an inductor and an inductance the same way. We're going to say that inductance has something to do with storage of magnetic flux. And so it will be amount of magnetic flux stored per unit what? Well, how do you store more flux in an inductor? Well, you need to make the B field in it stronger. And the way you do that is you increase the current through it. And so the inductance should be the flux inside the inductor per unit current running through it. A solenoid is probably the most common type of inductor, so let's figure out how to calculate the inductance of a solenoid. So we know that in a solenoid, the thing that's special is that it has a uniform B field, and it's just mu naught times the coil density times I, right? That coil density is number of coils per unit length. So let me write it that. Mu naught coils, number of coils, over the length of the solenoid. And so the flux, since that B field is uniform, it would just be B times A, except, remember, that field goes through N loops of the solenoid. And so you have to multiply that by the N loops that B field goes through. And so now we're pretty much done, because we can calculate our L. It's B times the cross-sectional area times N, all divided by I. And so the currents cancel, and we're left with just mu naught, the cross-sectional area, N squared over L. We should take a quick moment to talk about units. So that flux is in Webers. So we have Webers per amp as a unit of inductance, and this is called a Henry. And typical coils have inductances in the milli or microhenry range. And it's worth noting that a Weber we've seen is a volt second. So this is a volt second per amp, and a volt is a joule per coulomb, and a coulomb per second is an amp. So this is joules per amp squared, which suggests that the energy stored in an inductor must be something like the inductance times the current squared. We'll see that's almost correct. It's just missing a factor. So we know the consequence of Faraday's law is that an inductor will produce an induced EMF anytime the current through it is changing. So let's think about a solenoid like this with a current going through it, or in an alternate cross-sectional view with the currents coming out towards us at the top and in away from us at the bottom. And let's suppose that the current through it is increasing. Well, that means that the magnetic flux through it is increasing. And we know from Faraday's law that E fields are produced that would tend to drive currents to oppose that change in flux. In other words, if the current is increasing so that this B field would increase, the E fields would tend to point in such a direction that they would drive currents the other way. Or another way of thinking of it is that there is now an EMF opposing that change in the current. And we can just use Faraday's law to figure out what that EMF is. Note that the inductance is defined as flux per unit current, or in other words, we can say that the flux is just the inductance times the current, which I can put into Faraday's law. But the inductance is just a constant. It's a property of the inductor and doesn't change, so that can just come out in front of the derivative. And this is the relation for the EMF of an inductor. And note what the negative sign is just saying. It is saying that by Faraday's law, this EMF always tends to oppose changes in current through the inductor. Let's just think more about that sign convention and how it works out when we're tracing a loop in a loop law using Kirchhoff's loop law. And let's compare with a resistor. Let's suppose we are tracing around a loop and we are thinking of walking through this way with the current. Then we've seen that the delta V we would write down in our loop law expression would be realizing that as we go through this resistor with the current, we're going from high potential towards low potential, and so this is a negative potential difference. We usually only write Ohm's law as delta V equals IR, but there's a sign convention that if you're tracing in the direction of the current around a circuit, then there's a negative to indicate that that's a negative potential difference. Now, suppose you're doing the same thing, tracing through a circuit going in the direction of the current. If you are tracing through an inductor and the current is increasing, then that means that your current is positive, your di by dt is also positive, and the EMF expression we have here tells us that delta V, or the EMF across the inductor, is going to be negative again. In other words, you're going from high to low potential. Or it's behaving just like a battery pointing this way, which makes sense. That's a battery opposing the increase of the current. Similarly, if you're going through and the current is decreasing and you're going through in the direction of the current, then The current is positive, but di by dt is now negative, and so that makes the EMF come out positive, which says that you're going through a potential difference up in potential, and so it's behaving just like a battery pointing this way. In other words, a battery trying to keep the current going, which is what we know an inductor does. Time to check your understanding. So here's a simple circuit with a battery, an inductor, and a resistor, and there's a current flowing as shown, and that current is constant. And we've learned about walking around a loop to write Kirchhoff's loop law, so you would be going around the loop and writing down a series of potential differences, which you know add up to 0. And as you do so, you have to write down a potential difference across this inductor. Well, is that potential difference positive or negative, or is there no potential difference at all?